Alright guys, here we go. So, we're going to talk about the ratio and the root test. This is actually 9.4, this is 9.6, I'm sorry, 9.6. The ratio and the root test. Today we will not be doing the proofs for either one of these, so if you're interested on the proofs, I'm sorry, you're going to have to do another search on YouTube for find that proof, okay? What I'm going to do is I'm literally just going to give you what they look like and we're going to apply them, okay? So the very first one, let's talk about the ratio test. We're going to let an infinite series be a series with non-zero terms. Okay, what does that mean? Every term in the series can be positive or negative. As long as he doesn't have any of the terms being zero, you're okay. So this is your very first test after the alternating series test that allows you to have negatives. So this one's allowing you to have negatives as part of the terms. It just doesn't allow you to have any zeros. Cool? So if it does meet that requirement, we can do a couple things. First of all, the infinite series a sub n is absolutely convergent if the limit as n approaches infinity of the absolute value of the a of n plus 1 term divided by the a of n term is equal, it's less than, 1. And we'll talk about what that means here in just a second. Okay?
Wait, what?
Just stay with me. We'll talk about it here in just a second. Okay? So we have an infinite series. It doesn't have any zero terms, right? It will, and here's key. Not only does this test tell you that it converges, it tells you that it absolutely converges. Okay? But it absolutely converges if you were to take a limit as n approach infinity of the absolute value of the a of n plus 1 term over the a of n term. If you take that limit and that happens to be less than 1, then we can say that it absolutely converges. Okay? Yes?
Absolutely. Does that mean, like, basically for every single term, the n plus 1 term is going to be less than the n term?
Not necessarily. It just says that it's the next term. That's it.
Okay. But does that means it's only for it to be less than...
No.
That means it's increasing.
Let me do an example. It doesn't have to, guys. Okay? Stay with me. Number 2. If the infinite series a of n diverges, if the limit as n approaches infinity of the absolute value of the a of n plus 1 over a of n term is greater than 1 or is equal to infinity. Number 3. The infinite series what's that?
I wasn't here when you talked about absolute and conditional convergence. So is there an absolute and conditional divergence?
We literally just talked about that today, Zach.
I was out.
Oh, I'm sorry. I was like, I was like, dude, we talked about this 10 minutes ago. All right. I will explain to you here in just a second what that means.
Okay, but is there one for divergence too?
No.
Okay, that's all.
No, there's there's not such thing as absolutely diverging. Okay? All right. Number 3, actually, let me rewrite. It doesn't make sense to start that way. The ratio test is inconclusive if the limit as n approaches infinity of the absolute value of the a of n plus 1 over a of n term is equal to 1. So basically, as you can see, it's the same thing. It just all depends on the result. If it's less than 1, it absolutely converges. If it's greater than 1 or infinity, it diverges. If it's equal to 1, the test is inconclusive. It doesn't tell you anything. You got to try something else. Okay? This test is particularly useful for series involving factorials.
Oh, that makes sense, because the n plus one and
So, what that means is, personally, if I was running into just a problem that's asking about convergence and divergence, and it's dealing with factorials, this is probably the one that I'm going to try first. Okay? Here we go. Let's do an example. So we're going to determine the convergence and the divergence, or the divergence, I'm sorry. And let's say that you have a series from 1 to infinity, so it's an infinite series, of negative 10 to the n power over 4 to the 2n plus 1 times 2 plus 1. Okay, so I didn't tell you what test to use. Really, it's up to you what you want to do. But personally, what's the first test you would try? The nth term test, right? So if you were to try the nth term test, we'd have to take the limit of this, right? And then we have the limit as this gets bigger, right? And then this gets bigger and this gets bigger. So what do you guys think?
I think it doesn't tell you anything, because there's no way it equals 0.
I mean, this thing is looking a little complicated. You agree? Like just taking a limit. So we might have to do some L'Hopital here. And then taking derivatives of this, I'm seeing like not only that I have a product rule at the bottom, but what else is it that's going to bother you taking the derivative of? An exponential function. And it's not that you've forgotten, right? You totally remember how to do those, I hope.
Yeah.
It just gets a little complicated. So maybe we can go a different route. Agreed? Okay. Is this alternating? Negative 10, right? So could we attempt to use the alternating series test? But we also have to take the limit, right? So could we try the ratio test?
Oh yeah, let's try it.
Right? I'm not saying that all the other ones are not useful. I'm just trying to walk you through my reasoning here, and you're like, hope you understand why I'm skipping all this tests. The n-term test, I was like, okay, I'm going to take the limit, but I'm going to have to L'Hopital and et cetera, et cetera. And if it ends up being 0, then it's told me nothing. So I'm kind of, I don't know if I'm going to waste my time going in that direction. Okay? Then the alternating series test kind of makes me take another limit, so we got an issue there. Not an issue, but again, I'm trying to find the fastest way of dealing with this, right? Now, all of the other tests require that they're positive, and I'm going to have some negatives in here, right? So the only one that I'm left with as of today is the ratio test, right? Now, the ratio test tells me that I still have to take a limit. But look at what you got to take the limit of. The limit as n approaches infinity of the absolute value of the n plus 1 term, right, on top. What's the n plus 1 term? Well, you literally plug in n plus 1 for n. Everywhere you see an n. You guys with me? And then what does the ratio test tell you to do? Divided by the a of n, which is the original. Agreed? Isn't then a fraction divided by a fraction the same thing as multiplying by the reciprocal? So could I multiply by the reciprocal, which would be 4 to the 2n plus 1 times n plus 1 over negative 10 to the n, and we got absolute value there. Now, you should be looking at this, give me just a second, and you're like, I don't understand how that made anything easier. You just made this an insane looking limit. However, you actually did the total opposite. You made this a lot simpler if you remember your rules from algebra. For example, do you remember here, you can rewrite that as multiplication of two terms?
Negative 10 to the n times negative 10
Negative 10 to the n times negative 10
to the n.
to the first. Why? Because if you were to go the other way, when you have the same base, what do you do to the powers? You add them, right? So we're going backwards, okay? So we have that, and then we have that. Now, down here, do you guys see how if I simplify things out, this would be 4 to the 2n plus 3? Do you guys see that? Right here? Could I do the same thing? 4 to what power? Times what? 4 to the third power. And then this actually becomes what? N plus 2. Agreed? Stay with me. Hold on. Give me just a second. Can I apply those rules here as well? What does this become? 4 to the 2n, 4 to the first, n plus 1, and then I still have down here a negative 10 to the n power. Now I'm writing everything out because it's an example. What do you notice? Negative 10n, negative 10 to the n. 4 to the 2n, 4 to the 2n. Technically, this 4 to the first can cancel out this and make this into a 4 squared. Agreed? So here's what I'm left with. The limit as n approaches infinity of the absolute value of negative 10 times n plus 1. Agreed? So now that's gone and now that's gone. And on the denominator, I'm left with 16 n plus 2. And I really like what I see there. Because what's the limit of that? Absolute value of it, it will be 10 over 16, which is 5 over 8. So here's my question. The answer is 5/8. 5/8 is what with respect to 1? Less than 1. Therefore, the infinite series, what? Absolutely converges. Yep. Okay. Do you guys see why I chose this test? Do you see my reasoning behind? So this ratio test not only is very helpful with factorials, but I want you to look at the expression. I had a bunch of crazy powers going on. You see what I'm saying? Like this power to 2n plus 1. It could also be helpful when you're dealing with a lot of variables in powers per se. You with me? Okay, any questions on this one? Alright, let me pause this video real quick. Alright, we'll continue. So example number 2. We got the infinite series from 0 to infinity. That makes no sense, the infinite series from 0 to infinity. Wow. Okay. We got the infinite series of n factorial over 5 to the n power. The moment I saw the factorial, right away I was like, okay, I'm going to try the ratio test first to see if it works. Cool? So you tell me, I'm going to take the limit as n approaches infinity. The absolute value matters a lot. Of what? Good. N plus 1 factorial over 5 to the power of n plus 1 times the reciprocal, right? Which would be 5 to the power of n over n factorial. And I'm really happy to see that a lot of things, or a couple things here are going to cancel out, right? For example, n plus 1 factorial is the same thing as n plus 1 times n factorial. And then the 5 to the n, I can leave it as is. But on the denominator is going to become 5 to the power of n times 5 to the power of 1 times n factorial. And we got absolute value of that, right? 5 to the power of n's cancel out. N factorials cancel out. We are left with the limit as n approaches infinity of the absolute value of n plus 1 over 5. What does that equal to? Infinity, right? Therefore, the series diverges by the ratio test. This is actually one of my favorite tests because a lot of things just clean up very, like, it looks very complicated. It's one of those things that, like, when you watch a movie, you see a lot of work, and you're like, man, that person's really smart. And then if you really understand what's going on, you're like, oh, that was so easy, right? It looks complicated, but once things start cleaning up, you're like, okay, that was a pretty easy limit to take care of, okay? Do we get the idea of what the ratio test, how it works? Now, technically you have one where it fails, where it's equal to 1, but literally you're just going to have to try something else. That's really what it's going to tell you to do, okay? You would try something else, so you would go through your list and be like, well, maybe I can try the alternating, or maybe I can try the integral test, etc., etc. Cool? Will there be anything that fails all of them? No, you'll always find something to work. Like, you'll find a test that will work for someone. It may not be easy to determine, but it will work, okay? Yes?
So does ratio test only tell you if it's absolutely convergent or divergent?
Correct.
Not
Conditionally convergent? No. Cool?
Because there's only one case where it doesn't converge.
Exactly.
Hey, so what if it's a condition,
If it happens, here's what happens. You might try this test, and it might equal to 0, and then you might try another test, and it actually tells you that it converges, but what does that tell you about that series then? That it doesn't absolutely converge, that it only conditionally converges. So you can kind of use it on that manner if you want to kind of think about it that way. So if it fails this test, and then you try another test, and it does pass for convergence, what it really means is that that series conditionally converges. No. Okay. Are we good? Okay, so let's move on to something called the root test. And the root test is actually very, very similar. So once again, I am not going to go over the proof for this. So the root test. I'm actually a little lazy to write this all over again, so I already have it on my paper, so let me reflect it. The root test tells you the following. So let me just kind of enlarge this. So I'll go ahead and pause the video, and then when you're ready to go, just hit play. Alright, once again, let me clarify this. I mean by this, it has to be greater than 1 or infinity. Okay, I don't mean 1 over infinity. Okay, so if the limit is greater than 1, or if the limit is equal to infinity, then it diverges. Okay, so let's try an example. Say that you got the infinite series of 5n minus 3n to the third over 7n to the third plus 2 all to the nth power. We're going to start out with one that should be very obvious why I'm going to use the the root test, nth root test. Can anybody tell me why it would be obvious to use the nth root term test? Because I got it to the power of n. So if I do this, the limit as n approaches infinity of the nth root of 5n minus 3n to the third over 7n to the third plus 2 to the power of n, and we're doing absolute value of that, right? The root cancels the power, leaving you with the limit as n approaches infinity of the absolute value of 5n minus 3n to the third over 7n to the third plus 2, and you should be really happy with what you left over. What's the limit? 3/7. Because of the whole idea that the powers are the same, right? Don't forget those rules. Otherwise, you're going to sit here and do L'Hopital's rule a few times. Right? What does that mean?
it converges, absolutely.
Therefore, it absolutely converges by the root test. Cool? Alright, last example of the day, and then we'll call this We'll call it a day, okay? Sample number 2 for the root test. Okay, I left this for last for a reason. Let's talk this through as to, we kind of mentioned that the ratio test is helpful for factorials, but it could also help us for exponential functions, which is what I'm running into, right? Now, in the previous example, we had a power of n, so we use the root test because we're able to cancel that, right? So I can kind of see how I can use either one. Do you see it? Do you see how I can kind of use, or do you see the reasoning why I would maybe think of using either the ratio or the root test? What do you guys think? Okay, so that's a good idea. So could we rewrite it in a form like this one? Because if we can, then we can just use the root test and it cancels the n and we're good to go, right? So I'm looking at this, and is there a way to do that though? Yes.
Yeah, couldn't you just separate it as n to the power of n over 3 to n times 3 and then bring out the
So to write it like this, n to the power of n over 3 to the 2n times 3 to the first, like that?
and bring out the 3 and then put the n.
So bring out the 3.
And kind of with your,
If I bring out the 3, you mean like 1/3?
yeah, 1/3, sorry, yeah.
Okay. And then I would be left with that.
And then just do n over 9 to the power n. Sorry, is that the 2n or the 3n?
2n.
Okay.
Okay, I want to make sure I didn't lose anyone. Because I technically have 3 to the 2n, but a power to a power, you just multiply them, right? So if I do 3 squared, I get 9, right? Okay, now what?
Then you can do take the limit of
Of the n root of the absolute value of, which is 1/3 times the limit as n approaches infinity of the absolute value of what?
n over 9.
Which would give you what? Would give us what? Infinity. So you would say divergent, right? Okay. Okay. So let's talk this through because it is not divergent. Okay, so we're gonna keep this and we're gonna solve it a different way, and we're gonna discuss why we got divergent here. So we'll come back to it. Okay, so mathematically, I mean, do you think we did the right steps mathematically speaking? Yes? Okay. And this was using the root test, right? Okay. Yes, it's not correct.
Wait, how do you know?
Okay. You don't, so like I'm trying to right now, there's no way for you to know that, so I'm trying to show you why we got it wrong here in just a second, okay? So let's say we're starting back up with this problem, right? And you did want to use the root test, right? Like you did. So I'm going to use it, and I'm going to show you how I'm going to use it so that we're not making so many changes. We made a lot of changes. Do you guys agree? Like we kind of changed a lot of things. We follow algebra, but we made quite a bit of changes. So what I'm going to do is, instead, I am going to do the nth root test. Which means I would have to do that, right? Now, make sure that you understand this. Are you okay with what I did there? Because, like, for example, you have a square root that's to the power of 1/2, a cube root is to the power of 1/3, so the nth root is to the power of 1 over n. Algebraically, doesn't it allow you to take the numerator to the power and the denominator to the power? Bless you. So, what do you do when you have a power to a power? So what's n times 1 over n? So that would be n to the first power. Agreed? Over. Oh, you know what? Okay, I'm going to continue. You guys were right. Hold on. But we're going to continue because you are right. I'm looking at this and it is going to be infinity. Hold on. So I apologize, but let's kind of make sure. So, sorry. If I do this power to that power, I have to multiply, right? So I'm going to go to the side. That will be like 2n plus 1 times 1 over n, right? Which would be what? 2 plus 1 over n, right? So that would be 3 to the power of 2 plus 1 over n, and then the absolute value, right? Yes, 2 plus 1 over n. Now, if you were to do the limit, do you guys agree you're going to get like infinity here on top? So that'll be infinity over. Now, if you plug in infinity here, 1 over infinity is approximately 0, plus 2 is approximately 2. 3 to the power of approximately 2 is approximately 9, right? So I apologize. You are correct. Therefore, diverges by the root test. I'm sorry. So no, we did do the correct. I just felt, I'm going to be honest with you, I kind of felt like I never thought about doing it the way you guys kind of went about it on the previous one. I felt like we made too many changes, but I agree with you. Like I was kind of questioning, algebraically we did everything okay. Like we didn't break anything algebraically. Like there was nothing wrong with us pulling out the 1/3. There is properties that allowed us to do that. There's a property that allows us to break the 3 to the 2n to 3 to the 2 to the n power, which allows us to pull out the n, and then 3 to the 2 is 9. So if you saw it this way, which I'm going to be honest, I personally did not see it this way, it still worked out, right?
And will that way always work out, or should we just do it?
No. Then as long as, so basically what I'm going to conclude based on this is as long as you follow your algebra and everything algebraically is correct, you should be okay. Cool? Both of those ways use the ratio test. The root test, I'm sorry. What about if we were to try to use the ratio test? Could we attempt it?
Yeah, because the n to the n.
So let's try it and see what happens if we were to use the ratio test. So we're starting at 1 to infinity. Okay. I know. So I'm just kind of trying to show you my reasoning here, okay? So let's say that you wanted to use the ratio test, and that's what you decided to do, right? If you decided to do that, you would get that the limit as n approaches infinity of the absolute value of n plus 1 to the n plus 1 over 3 to the 2n plus 3, basically, after you simplify, times the reciprocal, which would be 3 to the 2n plus 1 over n to the n. Okay? So now, limit as n approaches infinity of the absolute value. Okay, first of all, the 3 to the 2n's are going to cancel out. Do you guys agree? Which will leave you to 3 to the first and 3 to the third, which is technically 3 squared, which is a 9 on the denominator, right? So that's gone and that's gone. But I'm not going to be able to cancel this out. You guys with me? Like there's... So this is what we will be left with, right? To take the limit off. So this is where it gets a little tricky now, right? Because it's like infinity plus 1, which we can do, to the infinity plus 1, which really, we're talking about that it's just some very large number, right? But then on the denominator, I still have like infinity to the power of infinity, right? And then we can get into this whole conversation. Well, isn't that technically the top one growing faster because of the plus 1, blah, blah, blah. Now we're kind of just assuming things. And the whole idea of the test is not to assume things, right? What's that? Could we try L'Hopital?
How do you derive
Well, we could try L'Hopital's, but then I'm looking at it. This is what I'm telling you. This is why I tried the ratio test, but I got here and I'm looking at it. I'm like, you know what? I don't know if it's worth it because I'm in a L'Hopital, and it doesn't look very pretty to use L'Hopital's here. I'm just trying to show you, because we're done with all the tests, how I'm kind of going about tests. Sometimes you're not going to pick the best test on the first try. So this is me saying, like, if I try this and I got here, I'll be like, I don't really I'm not very convinced that I'm getting anywhere. I'm going to try something else. And as we saw earlier, the root test worked out for us. So I would probably try the root test, okay? But this is just me kind of trying to show you how to approach some of these problems now that you know all the tests, because now you do. Now you know all the tests, so I'm no longer going to tell you have to use this test. I'm literally going to say, does this converge, does this diverge? Back yourself up by explaining which test you used. Okay? So that brings us to an end as far as this lesson goes. I want to show you something real quick before I let the video go. If you use this textbook, which we do in this class, there is a nice summary of everything we've done for the past 6 units in page 600 and I think it's 22. No, 632. So for those of you in my class, there is this chart in there. And this is a summary of every single test we've talked about. It tells you the name of each test. It tells you what the series look like. It tells you what the conditions are in order for you to use that test. It tells you what the conditions are for if it's going to be divergence or if it applies. And then some additional comments to talk about. Like for example, look, the entrance test, it says, this test cannot be used to determine convergence. We already know that, right? And down here, like we talked about the alternating series, hey, you can use the whole idea of the remainder, so they're reminding you that. And then this one's the ones we talked about today. Hey, you know what? The root and the ratio test is inconclusive if it's equal to 1. So it's a nice summary of everything we've done. Worst case scenario, you've been sleeping in this class for the last 2-3 weeks. This is going to save you, hopefully. Cool? All right.